Thanks everybody for attending this morning. Our focus is WGS84 versus NAD83 and some considerations that we need to think about in terms of these two geodetic datums. And then we talk about a little bit about why we care, because we used to really not care about this very much, but now it's becoming more and more important that we are aware of differences between these and the impact that it might have. And while this is really kind of this is mainly focused on GeoSync Go Cloud and the application applications that are using GeoSync Go Cloud, this also applies to any other mobile mapping or cloud-based mapping solution, or if you're using any of the GNSS GPS receivers, all this still applies in the same way. Well, first, a geodetic datum. Both WGS84 and NAD83 are geodetic datums, which means that both of those are coordinate systems, which is a set of reference points that we use to locate places on the Earth. Well, that's really important if we're using any kind of web map or GPS. We need to be able to find positions on the face of the Earth, and we see those positions primarily in latitude and longitude and elevation. So both WGS84 and NAD83 are both datums, so they're both coordinate systems, and both of those are widely used in terms of mobile mapping or any sort of GNSS data capture. Again, just a little bit more about coordinate systems, WGS84 and NAD83. So some things about that. Both of these are in use, but if we look at the Global Navigation Satellite Systems, or GNSS, both WGS84 coordinate system and NAD83 coordinate system are used. Both of those are used, and that can create some confusion from time to time that we're going to talk about a little bit more, in considerations that we have to take into account. So that the GNSS receivers are working, at least the output is either in WGS84 or NAD83. And we look at web mapping such as Google Maps, we think about that. Those maps are in WGS84 reference. That's the coordinate system that it uses. So if you ID a point in Google Maps, it's really providing that coordinate back in the WGS84 coordinate system. The other thing that's important is local GIS or mapping sources, really in the United States or most anything in North America, is all going to be the reference frame that it's using, or the coordinate system that it's using, is NAD83 almost exclusively. So even in Kentucky, where we're located, really everything from on the local level and the state level is really referencing NAD83. So again, why do we care? Why does this make a difference? So like I said, for years we did we've been working with GPS and GIS mapping for 25 years, and for the most part we really just didn't care very much about this. The differences didn't really matter. We didn't worry about that very much. But things have kind of changed, and some of the things that have changed that really make a difference here are positioning accuracies. And those accuracies now have improved significantly due to technology advances. So used to, and if we were using Google Maps, we were rarely really worried about real accurate information. It's more general. And then we were using that with the phone, the GPS in our phone, or a tablet, and it's not very accurate, so we don't really worry about that. But now, with the advent of GNSS receivers that can work worldwide, we now have the ability to get much more accurate positions, and then the web mapping technology has improved dramatically. So now we're beginning to use web maps for a lot greater detail than we used to. So we have to begin to care about whether we're working in WGS84 or NAD83. Originally, these two datums were equal; exactly the same. But now, over time, they've grown apart. So they're not really equal. So the difference in the continental United States, for example, in Kentucky, the difference is about a meter. So the difference in the coordinate published or coordinate calculated in WGS84 versus the same point calculated in NAD83, the actual difference in those coordinates is about 1 meter or 3 feet on the average in the United States. And that could be a big deal in some situations depending on the scope of the work that you're doing. So it's important that we're aware of it and we take it into consideration. Again, in the past, we really didn't worry about that very much, but now we have to begin to think about it. So when does it really matter for us? So let's just kind of run through this. It really matters mostly when we're based on how accurate we want our positioning to be. So if we use an autonomous GPS position or GNSS position just out of a receiver with no correction to it at all, we might be plus or minus 20 feet. And really in that case, we really don't care. For all practical purposes, WGS84 is equal to NAD83, no reason to worry about it. Even if we're doing some correction, but our accuracies are in the 10 feet range, 10 to 15 feet, I mean, we really still don't need to care about it very much. It's not worth the effort to really dig in and worry about the differences. When we begin to get into this 1 to 3 meter range, let's say somewhere between 6 feet to 10 feet in that range, then maybe we need to begin to think about it, because the difference between WGS84 and NAD83 is about a meter, and when we begin to get into that range, we got to think about it. Certainly today, because we can now use technology that we can capture information that is sub-meter or less than 3 feet, or even sub-foot, or now centimeter, which is survey accuracy, which is less than 1/10 of a foot. Now we have to really begin to concern ourselves about what datum coordinate system are we really working in, because if the difference in those coordinate systems is 3 feet, then that becomes a big deal. If I'm trying to map it sub-foot and I'm in the wrong coordinate system, all of a sudden I can interject errors that are on the order of 3 to 4 feet, depending on where I am in the United States. So just run through a few definitions. We've already said WGS84 is the World Geodetic System, 1984. NAD83 is the North American Datum, 1983. ITRS is a term that really, for me, I just here recently, as we've had to begin to deal with this, has showed up. For me, I really wasn't that familiar with before, but that's the International Terrestrial Reference System. And that would be for a sort of worldwide reference system, similar to what we have in the U.S. in terms of the monumentation that's maintained by NGS for North America. This is an international reference system that has control points all over the world, and they're published in WGS84. RTCM, Radio Technical Commission for Maritime Standards. RTK, DGPS is something that we will mention again, because that's differential GPS, and that's the method that we use in order to be able to get better positions, and that's a really important topic for us. And we've already mentioned geodetic datum, which is a coordinate system, and then the other thing that we work with are coordinate projections, and that is such as state plane coordinates or UTM coordinates, and that's where we take that datum, that coordinate system, and then we project it into a flat grid so we can put it on a piece of paper and work with it. And that may be the way we're most familiar with using coordinates and data. We're used to having that flat projected map. But underlying that is a datum or a reference system, and it's really important for us to know which datum system are we really working in. So a little history on this. NAD83, the North American Datum, 1983, is a successor to North American Datum 1927. So this is not anything new. We've had to have some sort of a coordinate system in North America, and NAD 27 has been around for a long time. It used an ellipsoid or a a model for the Earth, or at least for North America, and it served us pretty well. We had coordinates published all across North America that surveyors used and mapping folks used. But in around the mid-1980s, we needed a new datum, particularly when we began to see the GPS system that came into play. We needed a more accurate datum, something that was would more approximate the shape of the Earth. And so NAD83, the North American Datum 1983, was developed. Had a new ellipsoid called the GRS80 ellipsoid, and it was set up to really approximate as best it could the shape of the Earth. North American Datum 1983 does include more than just the continental United States. It's Canada, Mexico, the Caribbean, Hawaii, Greenland, and Central America are all included in the NAD83 datum. One thing that's really important as we get into this is that the NAD83 datum, the North American datum, is really anchored to the North American plate. So it's been optimized, it's been corrected, it's been adjusted. All the adjustments have been made to make it work as accurately as possible and for the best use for the North American part of the world in these nations that are listed here. So a little bit of history with NAD83 and what happened with that in the mid-80s. NAD83 was developed and was published. It had an ellipsoid where it was intended that the center of the ellipsoid would be at the center of mass of the Earth. It used the GRS80 ellipsoid. And then as they began to publish and adjust coordinates on known monuments, they began to find out that they needed to make some adjustments in that to really get that fit. So as we go forward from the mid-80s into the early 90s, we ended up with a hard network. So there was GPS surveying of all these monuments, and corrections were taking place. So we got better and better positions. And what they learned in that was that the actual center of that ellipsoid needed to shift a little bit. And then by the time we get to in the mid-90s, which is CORS, what they call NAD83 CORS 96, then in North America we established a whole bunch of continually operating reference stations, which were permanently connected and surveyed in with GPS. And at that point we really established what we would call NAD83 today. So from the beginning to when we get to CORS 96, the center of that ellipsoid on NAD83 shifted around some in order to get a better representation for the North American continent. And then since that time, the coordinate system has continued to be adjusted as there's better correction, better surveying to monuments. And then one thing that's really important, because it is fixed to the North American continental plate, as that North American continent drifts, then the published coordinates for NAD83 positions is changing based on the time and date. For the most part, we don't worry very much about those shifts, because for mapping and GIS, it's just not, the accuracy is not that important to us. But it is important to know that that NAD83 really does primarily reference back to the CORS 96 or to that point in time. So WGS84, on the other hand, World Geodetic System in 1984 was established by the Department of Defense in the mid-80s at the same time, and it was really set up to be exactly equal to NAD83. WGS84 was geocentric, so the point of it was to be able to have a worldwide system so that we could use this global positioning system in any place in the world and get and be able to get accurate positioning, so we could really, for defense purposes primarily. So the center of the WGS84 ellipse, or that model, is really geared toward the space vehicles or satellites, determine that in their rotation and all the physics that go along with that. And that continues to be the case. It's really is geocentric, and it's really geared to a worldwide system that is defined really by the space vehicles or satellites that are in orbit. The WGS84 ellipsoid is almost exactly the same as the ellipsoid for NAD83. There's very, very little difference and minor difference. So for all practical purposes, we're using exactly the same ellipsoid for both NAD83 and WGS84. So again, WGS84 did shift. There has been some minor adjustments over time, and when we talk about WGS84 today, we're really kind of referencing back into a point in time of around 2002, which is WGS84, or it could be called ITRF00, is really the primary reference for WGS84 coordinates. And then since that time, there are continual updates, and part of those updates happen because the center mass of the Earth is not static. It is dynamic, and it is changing, but the changes are very, very minor. So what's happened then is that over time, these two datums have shifted slightly. And again, we end up with a positional difference of about a meter in North America because of those differences. So some things to know about this that we want to know is GNSS or GPS, any of that is natively working in WGS84. So that's important. So if you have a GPS device and it is providing you a latitude and longitude, then it natively works with the WGS84 datum because it's capturing information from the satellites. It's using that ephemeris, and that reference frame or that datum is what it's using to calculate your position. That raw position is corrected and improved using a procedure called DGPS, or differential GPS, and that's the only way we can really get those positions into an accuracy that is, that's really useful to us in mapping, because the autonomous position is somewhere, or the native position is maybe 10 to 20 feet, and we often want to be able to get positions that are sub-meter, so we have to use DGPS to improve that position. GIS and project work in the United States is almost exclusively using NAD83. So if we're looking at all of North America, whenever we have a deliverable, that deliverable is almost exclusively going to be in the NAD83 datum. So the GPS work that we do natively is WGS84, but the deliverable that we have is almost always NAD83 in North America. When you have GIS and project work, design work that's going on outside of the U.S. or North America, then that work is primarily delivered in a WGS84 datum or data frame. There's several different DGPS methods that can be used to correct GPS positions. And so if you get a GNSS receiver, regardless of the manufacturer, you're going to find that you have, typically you'll have these type of options for doing corrections to improve that position into sub-meter particularly, or even sub-foot or better. And that's SBAS, which is satellite-based augmentation system. It's important to know there is SBAS is always working in WGS84. VRS, which is a virtual reference system, and in Kentucky, most of the states have a VRS set up. It's mostly set up for surveyors to use, but you can use that to do correction for your GNSS receiver. And the VRS is, in most cases, maybe not all cases, but in most cases, provides a correction to NAD83. So if we have a receiver that we're working with, a GNSS Bluetooth receiver, if we use SBAS correction, our output coordinates are in WGS84. If we're using VRS for correction, then our output is NAD83. Some other of the manufacturers, such as Trimble, have a subscription service, which is RTX subscription service, and that's now a worldwide service, and it is also providing corrections typically for WGS84, although there may be other options there to be able to get the output into NAD83, but generally it's important to know that that service is providing a correction for you that is in WGS84 coordinates, or at least you need to check with that service and see what output it is generating. The coordinate datum on the results of the mapping GPS data that we get is all dependent on the correction method. So we know that all GPS receivers or GNSS receivers collect data in WGS84, but the output that we really are going to use, the datum of that output, is always dependent on what the correction method is. So if I use SBAS, I'm going to get WGS84. If I use VRS, I'm going to get NAD83. And because these coordinate systems are different, we do need to be able to do transformations from and be able to have tools available to do that. So in the event that our output is in WGS84 and we need it to be in NAD83, then we need to be able to shift those coordinates. And those tools do exist. Some of the tool sources that you can use if you're using ArcGIS software, it does have tools that are built in to allow you to do that transformation between the two datums. Most of the manufacturers of GNSS receivers or GPS receivers also provide software that would do this transformation. And National Geodetic Survey, NGS, has tools. There's websites out there that will also provide those tools. So you can shift data between these two datums. You only really need to do that if the data that you're looking at needs to be sub-meter or better. Typically, that would be the sort of the dividing line. If your project scope requires you to deliver data in sub-meter or better, then you need to be aware of what is the output of the mapping that you've done. Is it in WGS84 or NAD83? And then, depending on what that output is, you need to then decide whether that matches to your deliverable or not. GeoSync Go Plus, the tool that's part of the GeoSync Go Cloud, if you're using it with a GNSS receiver, there are transformation tools and workflows built in and available that can help manage that transformation, such as if you're collecting data with using the SBAS correction, which produces a WGS84 coordinate, and you need that in NAD83, then there are tools in there that will help go ahead and do that behind the scenes and correct that position for you. Not all mobile software has that option in that. So if you're using a different mobile software collection platform, you just need to be aware of what the output is based on the type of real-time correction that you're using. So here are some scenarios that we would be dealing with here. So if the position that our output position is our coordinates that we get after they're corrected are in WGS84, and our deliverable is in WGS84, then we don't need to transform anything. We're good to go. So if my deliverable is a WGS84 deliverable, that's what my client says they want, or that's what my GIS is set up, or my local projects are set up in, and then I use the SBAS correction and get WGS84 coordinates, I don't need to do anything. I'm good to go. However, if I'm using SBAS and I correct and I get a WGS84 coordinate, but my output is NAD83, such as it might be in Kentucky if you were doing work for most any of the cities or any state agencies, then you would need to transform those coordinates from WGS84 to NAD83, and we would be seeing potentially a shift of about 1 meter. So the coordinates that came out of the GPS collection, when we deliver those, will shift about 1 meter in distance in order to get to NAD83. If I'm using GNSS receivers in the field and I'm using the VRS for my correction, so I'm using the state of Kentucky as an example. In Kentucky, I'm using the VRS system in Kentucky, then my output, the coordinates that I'm getting in real time, or corrected coordinates for the mapping I'm doing, are already in NAD83. And if my deliverable is NAD83, then I don't need to do anything. So as a good example, in Kentucky, if I'm working for almost any city or county and I'm using the VRS for correction, I don't need to do anything. I'm good. I'm in the same coordinate system that I need to be. However, if I were using the VRS and I had an international client who was maybe doing all of their work in WGS84, then I would need to know that and be able to transform those coordinates, because the NAD83 needs to be transformed to WGS84, and again, we have this about 1 meter difference. So some summary here and why this matters to us is that WGS84 does not equal NAD83. They're very close, but they're not equal. And the differences in the U.S. can average around 1 meter, and that varies depending on where you are in the continental United or in the North American area, but probably around 1 meter it would be a good average. Also, what's important is the output coordinate datum is dependent on the correction method that you used. So it's not dependent on the GPS receiver, it's dependent on the correction method that you use, whether that's SBAS, VRS, or some subscription service. The output is dependent upon that. There are transformation tools and workflows that do exist to handle this, but in order to figure out what the correct tool and workflow that you need to understand the scenario that you're working in, you know, what's happening in the field, what is my output, and then you also need to know what accuracy needs you have in order to know what type of transformation process you really need to deploy and use in your work. So that completes the webinar looking at considerations for WGS84 and NAD83. These are important, particularly as your accuracies get under a meter. When you're concerned about that, then you need to take this into consideration and put workflows in place that make sure that the quality of your data meets the specifications that you need. So thanks for attending today.